afternoon, everyone. I am PAVANI. I am from Department of Electronics and Communication Engineering, and today I am going to discuss about the chapter MTI and Pulse Doppler Radar. So this is from final year B.Tech semester 1. So here in this chapter we are going to learn about what is the MTI and Pulse Doppler Radar and what is the working principle of Pulse Doppler radar and how is it different from previous radars like continuous wave radar, and what is the working principle of MTI radar and what are the benefits of having MTI radar than the previous versions. So here we go. So why do we need to use the radar? Actually, radar receives the signal which is coming from the targets, okay, which is nothing but the echo signal. So these echo signals help us to find the range of target. So the targets may be fixed targets or they may be moving targets. So since we are discussing about MTI are nothing but Pulse Doppler radar, so those two seem to be same, but there is a difference. So here we are mainly concentrating on the moving target indication. That is why the chapter is named like MTI, moving target indication. So here our main concern is about moving targets. So when we use the radar, so it should receive only the echo signal which is coming from the moving targets. So which is our main criteria. So echo signal in the sense, so when you transmit a signal from the transmitter, it goes in several directions and it is stricken by the target and comes back. So the signal which comes back and received by the receiver antenna at the receiver is nothing but the echo signal, which is required signal. So here, since we are dealing with MTI, so moving target indication. So unlike fixed targets, moving targets move from one place to another place based on their relative velocity. So here we are concerning about the moving targets. So that is why moving target indication gains very much priority. But in practical applications, so it is very difficult to separate the targets from unwanted targets. So moving targets are our main criteria. So we need to receive only the signals which come from moving targets, and we need to avoid the signals which are coming from fixed targets. So those fixed targets, okay, the signals which are received at the receiver from the fixed targets, so those are nothing but the clutter. So which is nothing but the undesired, unwanted signals. So these are the echo signals which come from lands, seas, hills, and etc., trees, etc. So we have to minimize the clutters as less as possible, and we have to get only the desired echo signals which are coming from moving targets. So how do we do that? So what helps us to do that? So let us see. So when we select the radar, we have to select so it's such that it has to suppress unwanted clutters, and we have to allow only the desired signal which is coming from moving targets. So here we are stressing on moving targets. So why? Because here our main aim is to detect the echo signal from moving targets, which is nothing but our main target. Okay, so the unwanted fixed target should be avoided. So for this purpose, okay, to recognize the moving target, so the principle used in MTI or Pulse Doppler radar is nothing but the Doppler effect. So what is Doppler effect? So if you see the Doppler effect, so Doppler effect refers to the change in the wave frequency. So when it is in motion, okay. So when the observer and target, okay, when the observer is observing the target and how far it is from the observer. So if you just see that when the target is in motion with certain velocity, which is known as relative velocity, So sometimes it can be very high or sometimes it can be moderate. So in such case, so when the signal strikes the object, the target, and when it comes back, it undergoes some frequency shift. That can be either incremental or decremental. For example, how it can be incremented or decremented, let us see. So when you are the observer, when you are observing from the receiver side, so when the target is approaching towards you, so the frequency increases. So that here we have to add the difference frequency, which is nothing but the Doppler frequency, to the signal frequency which we have transmitted. So for example, if you take F0, okay, or Ft as receiver, transmitted signal frequency, so then if the moving target is approaching you, so then the Doppler shift can be added so that the remaining frequency, the resultant frequency, is incremented. So the incremental frequency will be Ft plus Fd. Okay, so this is the case when the moving target, okay, is approaching towards you. Okay, the plus sign should be added when the moving target is approaching you. Okay, so then the resultant frequency is Ft plus Fd. But in case if it is going beyond you or if it is going away from you, then there is decrease in frequency. So the decrease in frequency is just written as Ft minus Fd. So here Fd is the Doppler frequency which is subtracted from the transmitted frequency. So this is the case. In this case, the resultant frequency is decreased. Okay, so minus sign should be used in case when the object, okay, the required target is going away from you. Did you understand? So Doppler effect is nothing but the change in frequency which is especially allowed for only moving targets but not the fixed target. So here our main concentration is on moving targets. So if you see, so this is the principle we are using in Doppler radar or else moving target indication. Okay, so here the frequency shift which is going to be offered is given by the expression 2 times the relative velocity for lambda. Lambda is nothing but the wavelength of the pulse. Okay, so here we have to separate by using this Doppler frequency. We can separate the fixed targets from stationary targets. So our main concentration is to separate desired moving targets from undesired stationary objects. So these are the undesired stationary objects are nothing but the clutter. So which are fixed, which are not our concern. So we have to concentrate on the moving targets. So this shift is introduced only in the moving targets. So such type of radar which utilizes Doppler frequency shift as a means of discriminating factor, okay, is for deciding moving targets from fixed targets is called moving target indicator or moving target indication or pulse Doppler radar. So these two terms appear to be same, but MTI is a concept which can be used in the radar. So we have seen already what is Doppler effect, which is nothing but the frequency shift is introduced for moving targets to separate them from stationary targets. And here if you see pulse Doppler radar versus moving target indication. So moving target indication is usually refers to the moving target MTI usually refers to the moving target indication, which is nothing but the mode of operation in a radar to discriminate a target against clutter. So here this moving target indication is especially used in pulse Doppler radar. So this is the mode of operation. So it separates a target of our interest from the remaining unwanted fixed targets, which are commonly known as clutter. So in this technique, the pulse repetition frequency, okay, so is chosen very low so that we can avoid the ambiguities in range. So with this technique, we can clearly identify the range of the target. That means how far the object lies, okay, our target lies from the radar. Okay, but here we have to compromise with blind speeds. So blind speeds are the speeds so where the targets will not be seen by the radar. But here we are interested in the target, which is the moving target. So, but range can be seen, means it is how far it is from the radar can be easily determined. But the problem is sometimes due to its low frequencies, the blind speed, okay, at which the wave is approaching cannot be determined. So we have to compromise with relative velocity here. So, but in the case of pulse Doppler radar, so on the other hand, it has high pulse repetition frequency, so that there is no chance of blind speeds. So we can clearly determine the relative velocity with which it is approaching the radar. Okay, but there is a problem. There is ambiguity in the range. So we cannot determine the range clearly. So these are the two techniques used to determine the moving target, pulse Doppler radar or moving target indication. So in moving target indication, we can clearly determine the range, but we cannot determine how, with which velocity, what is the relative velocity it is approaching towards the receiver station. Whereas in pulse Doppler radar, we can easily determine the relative velocity with which it is approaching, but we are unaware of the range, what is the distance it lies from the observer. And if you see, this is the working principle of these are the two block diagrams which indicate the working principle and operation of the moving target indication or pulse Doppler radar. So if you see, there are two figures. So figure A represents the continuous wave radar which you have studied earlier. Okay, so this is one. So here if you look at the block diagram of continuous wave radar, so it contains simply three blocks. So one is continuous wave oscillator, so which generates the signals. Okay, so here from this oscillator we can generate the signals which are continuous waves, so with frequency ft. So can you see ft, frequency ft? So it goes in several directions, okay, and whenever if it detects the moving target, whenever it hits the moving target, it comes back and received at the receiver antenna. So since it is moving target, see, you can see plus or minus FD, which is nothing but the difference frequency. So FT plus or minus FD, so it is nothing but the echo signal received at the receiver. And at the receiver, mixer is present, so that mixer generates either sum or difference of the frequencies. So here the unwanted frequency components can be minimized. So which is nothing but the transmitted frequency ft can be cancelled out. This ft and this ft can be cancelled out, and only the difference frequency can be allowed to the indicator. So on the indicator you can see the signal, which is nothing but the range of echo signal, how far it is from it. And this is the previous version. This is the previous wave radar which we have discussed. But here, if you see, we can simply by adding two columns, two blocks, so we can make it pulse Doppler radar. So which is better than the previous version. So those two blocks are nothing but the pulse modulator and power amplifier. See, these three blocks are the same: continuous wave oscillator and receiver and indicator. So these three are the same, but by adding only simple two blocks, okay, it makes a better version. Okay, so since we have used the pulse modulator, it is known as pulse Doppler radar. Okay, did you understand why the name comes pulse Doppler radar? Because we are using pulse modulator here. So let us see the working of this pulse Doppler radar. As we have discussed in the continuous wave radar, here also continuous wave oscillator present. So it transmits the continuous wave signal with same frequency ft. Okay. So when it emits the signal, so immediately it will not be transmitted. So here we have another block which determines whether to transmit or not the transmitted signal. So here this pulse modulator turns off or on the power amplifier, so that whenever this pulse modulator turns on the power amplifier, then the emergent transmitted signal can be transmitted through the transmitting antenna into the space. Otherwise, whenever pulse modulator turns off the power amplifier, the signal cannot be transmitted. So that we can transfer the pulse gain here. Did you understand? So once pulse modulator turns on, the signal, the transmitted signal from oscillator can be transmitted to the transmitting antenna, and whenever it hits the moving target, it undergoes difference in the frequency, which is nothing but the frequency shift. That is known as that is nothing but Doppler frequency. Okay, so it is either incremented or decremented. So if you see here, ft plus or minus ft. So the increment, it can be incremental frequency or decremental frequency. So based on how the target is approaching. If it is approaching towards you, this resultant frequency will be ft plus fd. Or if the target is going beyond you, it is nothing but it takes a value of ft minus ft. So this is the resultant echo signal which is of our interest. Okay. So this signal is nothing but the received echo signal from moving targets. So sometimes it may contain the cluster. So here we have to eliminate the cluster. Okay. That work is done by the receiver. So here at the receiver we have two separate signals. Okay, one is the reference signal which is obtained from transmitter, and the other one is echo signal which is received by the receiver antenna. So in the receiver we have mixer. So this mixer generates either sum or difference of the frequencies. So here ft can get cancelled and the required Doppler frequency signal is transmitted through the mixer. Okay, so here, unlike in continuous wave transmitter, so we have an advantage of having this reference signal. So what it does, so actually using this reference signal, we can preserve the phase. It acts as coherent reference signal. So okay, so coherence means preserving its phase. See, let me show you the equations. You see, this is the echo signal which is received at the receiver. So which is given as its voltage is given as V echo equal to A3 sine 2 pi ft plus or minus ft minus 4 pi ft r0 by c. So what is this here? This is the voltage of the Doppler shifted echo signal. And let me show you another one. The reference signal. Wait, here. So if you see, this is the difference voltage which is obtained from the mixer. So in the mixer, as I discussed earlier, the reference frequency ft and the transmitted frequency will get cancelled and the resultant difference frequency is obtained. And if you see here, see, minus 4 pi ft r0 by c. So this is the phase of the difference signal. And I have shown you previously what is the phase of the echo signal received with the receiver. This is the phase of the received signal at the receiver. So same, 4 pi ft r0 by c. Check once more. So this is the phase. So there is no change in the phase. This is nothing but the coherence. Did you understand? So that is the advantage of moving target indication continuous wave oscillator. That is the job done by the continuous wave oscillator in the moving target indication. So here if you look at the operation, so this is the moving target indicator on pulse Doppler radar. So a simple continuous wave radar which you have studied earlier, so can be converted easily into pulse radar by simply adding power amplifier and pulse modulator to it, okay, which generates the pulses. So whenever pulse is generated, it transmits it. Whenever pulse is generated, the transmitter transmits the signal into the space. Whenever pulse modulator turns off the power amplifier, it will stop the signal. So there is no transmission of the transmitted signal from the transmitter. And as I have discussed earlier, so here in the case of MTI or pulse Doppler radar, continuous wave oscillator, okay, acts as coherent MTI radar. So by coherent, so it acts as a coherent reference needed to detect the Doppler frequency shift. So as I said earlier, continuous wave signal does more than the job of the local oscillator. So it acts as the coherent reference needed to detect the Doppler frequency shift. So this type of advantage is not available in continuous wave radar. If you look at this operation, so there is no reference signal, there is no coherence. So there is no chance of phase preservation in case of continuous wave radar. But if you look at here, so this reference signal from continuous wave oscillator preserves the phase of the signal, as I have shown you. So if the continuous wave oscillator voltage is represented as A1 sine 2 pi FTP. So as you know, continuous wave means, so it is in the form of sinusoidal. So that is why the expression is given as V1 equal to, okay, A1 sine 2 pi Ft into T. So A1 is the amplitude of the transmitter signal, Ft is the carrier frequency, okay, and T is the time period of the transmitter signal. And if you see the reference signal voltage, so this is the reference signal voltage which is obtained from the continuous wave oscillator, which acts as a coherent difference. So here V reference equal to A2 into sine 2 pi Ft into T. So A2 is the amplitude of the reference signal, so which is nothing but a sinusoidal wave again. So Ft is the transmitted frequency and T is the time period. And if you see, this is the V echo which is received at the receiver. So its voltage is given as V echo since it underwent the frequency shift. So V echo is equal to A3 sine 2 pi Ft plus or minus Ft into T minus 4 pi Ft R0 by C. So here V echo is nothing but the voltage of the received echo signal at the receiver, and A3 is the amplitude of the received signal, and Ft is the transmitted signal frequency, and plus or minus. So plus or minus is decided by the how, in which direction, whether it is moving towards the receiver or moving away from the receiver. So Fd is the Doppler frequency and T is the time period, and R0 is the range, okay, at which the signal is received. Okay, this indicates the range of the signal, how far the moving target lies from the radar. And as I have mentioned earlier, so the reference signal from continuous wave transmitter and the echo signal which is received at the receiver, those two can be heterodyne. They are mixed, they are combined in the mixture stage of the receiver. So only the low frequency, which is of our interest. Why? Because the frequency shift is very low which is introduced in the received signal are nothing but the echo signal at the receiver. So only we need this. This is the deciding differentiating factor, okay, from moving targets and fixed targets. So it can be transmitted to the mixer. So its expression can be given as V difference. So it is the voltage with which it is traveling. So V difference equal to A4 sine 2 pi ft minus 4 pi ft R0 by C. So where V difference is the voltage of the difference voltage, V difference is the voltage with which the resultant voltage, the resultant signal is traveling. A4 is the amplitude, and FD is the Doppler frequency, which is nothing but the deciding factor of moving targets. Okay, T is the time period with which the signal is traveling. Okay, and this is the phase with which the signal is traveling. So there is no change in the phase. This work is done by the continuous wave oscillator, which is present in the MTI or pulse Doppler radar. So those two, one and P, first equation represents the transmitted signal, okay, and the third equation represents the sine wave carriers upon which the pulse modification is imposed. Okay, the difference frequency is equal to the Doppler frequency. Okay, so always this is the FD is the deciding factor. Okay, which discriminates moving targets from stationary targets. So for stationary targets, the Doppler frequency shift will be 0. So there is no frequency shift for fixed targets because they are fixed. So there is no frequency shift introduced for the signals which are received at the receiver from stationary targets. Whereas V difference will not vary. It remains same for each and every sweep of the signal. And the amplitude can be constant and may take any value from positive A4 to minus A4, including 0 sometimes. Okay. So however, when the target is in motion related to the radar, FD has a value other than the 0. Okay. So when the target is moving, obviously it undergoes frequency shift, which is nothing but the Doppler frequency shift. So that is why it has non-zero value, and it has its own corresponding voltage, okay, from the mixer. So it is always the function of the time. So and if you see, these are some of the outputs which can be shown on ASST.Scope. ASST.Scope is the video display for seeing the range of the received echo signal. So the first pulse indicates a radio frequency echo pulse stream, okay, which is received. So it is traveling with the pulse interval tau, and this is the second figure indicates the video pulse strain for Doppler frequency greater than the reciprocal of pulse interval. Okay, so in this case, so in the case of the waveform which is shown in the figure P, so we can easily determine the information from single pulse. Okay, so the information can be decoded easily when the Doppler frequency is greater than the reciprocal of the pulse interval. Okay, so but when the Doppler frequency is very less than the pulse interval, so then it is not so easy to determine the range. Okay, so many pulses are needed to determine the range of the moving target. So as I have told you earlier, so the received signal from the moving targets, okay, can be seen on the ASST.Scope, which displays the function which displays this different sweeps in terms of voltage versus range. Okay, so here a single sweep on an ASST.Scope can be shown, or multiple speeds also can be shown. So if you look at this figure, so here you can see several speeds of the output indicated on the A-score. So figure A, figure B, C, D, E, F. So if you see, these are the sweeps. So this is the first sweep. So if you see this first sweep, so can you see the arrows indicating the moving targets here? So here, this is the received echo signal, okay, at the receiver, which contains clutter as well as interested moving targets. So here we have to suppress the clutter such that we have to take the continuous successive sweeps of different signals. So here these successive sweeps, so if you clearly notice here, so these two arrow marks indicate the moving targets, okay, so the others are fixed target. So if you observe the amplitude or voltage, so of each sweep, so if you observe the first portion here, so the voltage is not going to be varied in this portion and in this portion and in this portion. So there is no change in the voltage because they are the signals received from the clutter, okay. So because their voltage is not going to be varied because there is no frequency shift in there, okay. So V difference might be constant, which takes the value from plus amplitude 4 to A4 to minus amplitude 4. But if you see at the arrows, so these are superimposing on one another. Imposing, so they are traveling, their amplitude is slightly increasing or decreasing. So they are traveling like variable voltages, okay. So they will not maintain certain voltage. So their voltage is continuously changing, okay, which is nothing but the V difference voltage. So that is why you can see many portions, many sweeps on one on them, okay. Superimposition means one on another, okay. So you can see incremental voltage to decremental voltage or decremental voltage to incremental voltage. So like this, we can see the effect which is known as butterfly effect. So this butterfly effect is the indication that the target is moving, okay. So when the target is moving, its difference voltage is continuously varying. So that is why on a scope we can see different types of waves superimposing on one another. So that is this butterfly effect is the indication that the targets are moving targets. So if they are fixed, they are nothing but the fixed targets. Okay, successive A-scope sweeps, which I have shown you from 3A to 3E. So these are echoes from the fixed targets remain constant throughout, but echoes from moving targets vary in amplitude from sweep to sweep at a rate of corresponding to the Doppler frequency. So this voltage varies based on the Doppler frequency shift. So the superimposition of successive A-scope speeds is shown in figure 3F here. Okay, so this is nothing but the butterfly effect. Okay, which indicates us the target is nothing but the required moving target, but not the fixed target. Thank you.